The human brain frequently perceives phantom vibrations and ghost notifications as a direct result of modern sensory signal processing. This phenomenon reveals how our neural architecture adapts to digital tools. The somatosensory cortex continuously generates internal models of expected touch, which sometimes causes us to feel sensations that have no physical cause. Scientists refer to this as a tactile hallucination, where the brain creates a hit in the absence of a real external stimulus. This predictive processing is an efficient way for the body to stay prepared for important information. If you enjoy these relaxing facts, please consider subscribing to the channel. Our skin is populated by specialized nerve endings called Pacinian corpuscles, which are exquisitely sensitive to the specific frequency of a smartphone vibration. These receptors are designed to detect rapid changes in pressure and tension within the deep layers of the dermis. Because these nerves are always on standby, they can sometimes fire in response to the simple friction of clothing against the leg. The brain often struggles to distinguish between the microrhythms of a muscle twitch and the mechanical pulse of a haptic motor. When we are expecting a message, the threshold for what the brain considers a notification drops significantly. This lower threshold makes it much more likely that a random neural firing in the thigh will be interpreted as a digital alert. Research published in the journal Computers in Human Behavior suggests that nearly 90% of mobile phone users have experienced these ghostly pulses at least once. This high prevalence indicates that the brain is physically remapping its boundaries to include the devices we carry. We begin to treat the phone not as an external object, but as a functional extension of our own nervous system. Every time a device vibrates, it sends a specific electrical signal through the spinal cord to the thalamus for routing. Over time, the repetition of this specific signal creates a dedicated neural pathway that is easily triggered by similar non-digital movements. This is a form of science for sleep that explains why our bodies feel plugged into a network even when we are resting. The density of mechanoreceptors varies across the body, with the areas where we typically keep our phones being particularly sensitive to movement. Because the thigh or the wrist has a large representation in the brain's sensory map, even a slight shift in posture can mimic the start of a vibration sequence. This constant monitoring is a testament to how deeply technology has integrated into our biological frameworks. The feeling of a phantom vibration is often a sign that the brain is working exactly as it should by prioritizing potentially important signals over background noise. By filtering out the constant pressure of a chair or a waistband, the mind clears the way for the subtle, sharp pulses it has been trained to value. This selective attention is a fundamental pillar of human survival and modern communication. The brain does not simply wait for the world to happen to it. Instead, it constantly generates a proactive model of what it expects to feel next. This process, known in neuroscience as predictive coding, allows the mind to stay one step ahead of reality by anticipating sensory inputs before they actually arrive at the skin. By constantly simulating the immediate future, the brain reduces the amount of energy it needs to process the massive influx of data coming from the environment. This internal simulation is remarkably detailed, creating a mental draft of every physical sensation we anticipate throughout the day. When you expect a notification, your brain pre-activates the specific neural clusters associated with the feeling of a vibrating phone. These relaxing facts about our biology show how the mind prioritizes efficiency, often favoring its own internal predictions over the raw data provided by the peripheral nerves. A fascinating mismatch occurs when the brain's internal prediction is so strong that it overrides the lack of actual physical stimuli. If the predictive model is primed to expect a vibration, it may interpret a completely unrelated sensation, such as the shifting of fabric or a minor muscle pulse, as the anticipated event. This error in the brain's inference engine results in a vivid tactile experience that feels entirely real despite having no external cause. The flow of information in the nervous system is not just a one-way street from the body to the brain. While sensory nerves carry signals upward, the primary somatosensory cortex sends top-down signals back down the spinal cord to modulate how we perceive touch. These descending pathways can actually sensitize certain patches of skin, making the nerves in your thigh or wrist more reactive to the slightest movement when you are waiting for a message. At the heart of this anticipatory system is the prefrontal cortex, which acts as a conductor for our sensory expectations and goals. It communicates with the parietal lobe to create a spatial map of where we think our devices are located at any given moment. This constant monitoring ensures that we are always ready to respond, but it also creates the perfect environment for a ghost notification to manifest in the mind. Deep within the brain's architecture, the thalamus acts as a sophisticated gatekeeper, filtering out background noise so that important signals can reach conscious awareness. When we are in a state of high anticipation, the thalamus lowers its threshold for what it considers a significant signal. This neurological hair trigger means that even the faintest neural hum might be passed along to the higher processing centers as a confirmed vibration. The chemical environment of the brain also plays a critical role in how these predictions are formed and maintained. Neurotransmitters like glutamate and GABA balance the excitement and inhibition of the neurons responsible for mapping our sense of touch. When this delicate chemical balance is shifted by the habit of frequent device use, the brain becomes more prone to false positives in its sensory reporting. The physical boundaries of our bodies are more fluid than they might appear. Through a process called peripersonal space mapping, the brain begins to treat objects we carry frequently as if they were actual parts of our anatomy. This expansion of the body schema is why a phone in a pocket can feel like an extra limb, integrated into the same neural loops that manage our natural sense of touch. The brain's ability to anticipate the world is a testament to its incredible evolutionary history as a survival organ. By predicting the what and where of a sensation, our ancestors could react faster to threats or opportunities in their surroundings. In the modern era, this same high-speed circuitry has been repurposed to monitor the digital pulses that connect us to our social and professional lives. There is a subtle shift in the way the skin feels when it is in constant contact with a mechanical object. Over hours and days, the brain learns to tune out the static weight of a device while remaining hyper-alert for the specific frequency of its vibration motor. This selective tuning is a masterclass in biological adaptation, allowing us to carry complex technology without being overwhelmed by the constant physical pressure. The human brain possesses a remarkable ability to interpret the world through a series of complex internal models. One of the most fascinating expressions of this is known as phantom vibration syndrome, a widespread and non-clinical sensory phenomenon experienced by the vast majority of mobile device users. This is not considered a medical disorder, but rather a common byproduct of how our nervous system adapts to modern technology. When we frequently expect a specific tactile signal, our sensory cortex becomes primed to detect it, sometimes even in the absence of any physical trigger. A tactile hallucination occurs when the brain's internal expectation of a sensation overrides the actual data coming from the skin's receptors. In the case of a phantom vibration, the brain is essentially making an educated guess based on a high-probability event it has learned through repetition. The neural pathways responsible for processing touch are incredibly sensitive, and when they are in a state of heightened readiness, they can misinterpret minor physical noise as a structured signal. Imagine a person standing in a quiet hallway, suddenly feeling a distinct, rhythmic buzzing against their thigh. They instinctively reach down to check their pocket, only to realize their phone is sitting on a desk in another room entirely. The sensation felt real enough to trigger a physical reaction, yet there was no external force acting upon the skin. This brief mismatch highlights how the mind can generate a convincing physical experience based purely on anticipation and habit. It is important to distinguish these biological hallucinations from actual technological glitches or malfunctions within a device. A technological glitch involves a literal mechanical or software error where the vibration motor fires without a legitimate notification. In contrast, a phantom vibration is purely internal, occurring within the somatosensory system of the person. One is a failure of hardware, while the other is an overperformance of a highly adaptive and vigilant human brain. The mechanics of this experience rely on the brain's signal detection threshold being set slightly too low. Because we often value a notification more than we value being left alone, the brain decides it is better to report a vibration that isn't there than to miss one that is. This false alarm is a sign of a healthy, functioning system that is simply trying to be as efficient as possible. By prioritizing the most likely sensory outcome, the brain ensures it is always ready to respond to the digital world. The skin's surface is constantly sending a stream of data to the brain regarding temperature, pressure, and the movement of clothing. Most of this information is filtered out long before it reaches our conscious mind, allowing us to focus on more important tasks. However, when we are waiting for a message or a call, the brain pulls this background data forward, searching for anything that matches the frequency of a phone's motor. When the brain identifies a match, it projects the sensation back onto the specific area of the skin where we usually carry our device. This projection is so precise that we can often pinpoint the exact location of the ghost notification. It serves as a vivid reminder that what we perceive as the outside world is often a sophisticated reconstruction created within the dark silence of the cranium. The frequency of these phantom events often correlates with how much a person relies on their device for social or professional connection. As the brain assigns more importance to these digital signals, it devotes more neural resources to monitoring them. This leads to a refined sensitivity that can be both impressive and slightly confusing when the pocket remains empty. Despite the strange nature of feeling something that isn't there, the experience is generally fleeting and harmless. It represents the fluid boundary between our physical bodies and the tools we use to navigate our lives. By understanding that these sensations are a natural result of neural adaptation, we can appreciate the incredible depth of our sensory architecture. The brain's commitment to pattern recognition ensures that we are rarely caught off guard by the environment. Even when those patterns turn out to be internal echoes, they demonstrate the tireless work of the nervous system in keeping us connected to our surroundings. This phantom touch is simply the mind's way of staying prepared for the next moment of engagement. The human nervous system has spent millions of years refining its ability to detect the slightest changes in its immediate environment. This ancestral sensitivity was not developed for digital alerts, but for the fundamental necessity of survival in a world filled with hidden dangers. Early humans relied on a sophisticated array of mechanoreceptors to interpret physical vibrations that could signal the presence of a predator or a source of food. Long before the invention of modern technology, the skin served as a primary early warning system for the body. A faint rustle against the leg or the delicate movement of an insect landing on the arm required an immediate shift in attention. These tiny tactile cues were often the only indication that something in the environment had changed, necessitating a rapid neurological evaluation. In the ancient wilderness, failing to notice a subtle vibration could have dire consequences for an individual's safety. Therefore, the brain evolved to favor a strategy of overdetection rather than underdetection. It became biologically advantageous to occasionally feel a vibration that wasn't there if it meant never missing a movement that truly mattered. This deeply ingrained hardware for threat detection remains active in the modern world, though its primary focus has shifted. The same neural pathways that once scanned for the vibration of a crawling spider are now tuned to the specific frequency of a smartphone motor. Our brains have essentially repurposed ancient survival mechanisms to monitor the digital landscape for social and professional signals. When a device is kept in a pocket or held in the hand, the somatosensory cortex integrates that area into its high-priority monitoring zone. The brain begins to treat the phone as an extension of the body's sensory boundary, much like a tool or a piece of clothing. Because of this integration, the sensory system stays in a state of quiet readiness, prepared to catch the very first millisecond of a notification pulse. The modern experience of a ghost notification is a direct legacy of this hypervigilant evolutionary history. When the mind is in a state of anticipation, it lowers the threshold required for a sensation to be registered as real. This means that a minor muscle twitch or the shifting of fabric can easily be misidentified by the brain as the specific mechanical hum it is searching for. Evolutionarily, the cost of a false positive, feeling a vibration when there is none, is incredibly low, involving only a brief moment of redirected attention. However, the cost of a false negative, missing an important signal, could historically have been much higher. This imbalance ensures that our sensory systems remain biased toward detecting patterns, even in the absence of a physical stimulus. The brain's internal filtering system, known as sensory gating, usually prevents us from being overwhelmed by the constant pressure of our clothes or the air. Yet, when a specific signal becomes linked to a meaningful outcome, the gating mechanism adjusts its parameters. This adjustment makes us more likely to break through the noise of daily life to find the signal we are expecting. This heightened state of sensory awareness is not a static condition, but fluctuates based on our internal chemistry and external environment. The brain constantly recalibrates its sensitivity based on how rewarding or important it perceives a particular stimulus to be. As we navigate our day, certain chemical messengers quietly begin to reshape how we interpret the world against the skin. The persistence of these phantom sensations reveals how much of our perceived reality is actually an educated guess made by the nervous system. We do not simply feel what is there. We feel what we are prepared to feel based on a lifetime of environmental feedback. Our ancestors' need for vigilance has left us with a sensory system that is both incredibly precise and occasionally prone to imaginative errors. The transition from monitoring for physical threats to monitoring for digital pings has happened with remarkable speed in evolutionary terms. Our biology has adapted to these new tools by utilizing the same better safe than sorry logic that protected us for eons. Each time we check a phone after a phantom buzz, we are participating in a behavior rooted in the deep history of human survival. This ancient hardware is incredibly resilient, maintaining its watchful state even during periods of rest or distraction. It functions as a silent guardian of our connectivity, ensuring that we remain tethered to our social circles and responsibilities. The ghost notification is a byproduct of this tireless vigilance, a small glitch in a system designed for a much harsher world. As we move through our lives, the brain continues to fine-tune these detection thresholds with every interaction. It learns which vibrations matter and which can be ignored, though it rarely manages to eliminate the occasional false alarm entirely. This sensitivity is a hallmark of a healthy, adaptive nervous system that is deeply attuned to its surroundings. The interplay between our biological past and our technological present creates a unique sensory landscape for the modern human. We carry within us the echoes of a wilderness where every touch was significant, applying that same intensity to the hum of a battery-powered motor. It is a testament to the flexibility of the brain that it can bridge the gap between these two vastly different worlds so seamlessly. Understanding the evolutionary roots of this behavior helps to normalize the strange sensation of a phantom vibration. It is not a sign of a malfunctioning mind, but rather an indication of a highly optimized one. The brain is simply doing what it has always done, prioritizing the signals it deems most important for the individual's success and well-being. The mechanism behind this heightened awareness is deeply tied to how the brain calculates the value of information. Each potential notification carries the possibility of a social reward or a necessary update, which the brain tracks with extreme precision. This internal valuation system is what keeps our sensory receptors on high alert, even when the environment is perfectly still. The human brain possesses an incredible capacity to organize chaotic sensory input into meaningful structures. Most people are familiar with the visual version of this phenomenon, such as seeing a face in the craters of the moon or a shape in a passing cloud. This cognitive process is known as pareidolia, a term traditionally used to describe the tendency to perceive specific, often meaningful images or sounds in random or ambiguous stimuli. While it is usually discussed in the context of sight or hearing, the underlying neurological mechanics apply just as strongly to our sense of touch and the way we interpret physical vibrations. Have you ever wondered how the mind fills in missing physical information when a sensation is faint or interrupted? This process of tactile pareidolia occurs within the somatosensory system, which is the network of neural pathways responsible for processing touch, temperature, and body position. When the skin detects a subtle, ambiguous movement, perhaps the shifting of fabric or a minor muscle pulse, the brain does not simply record the raw data as a random event. Instead, it immediately compares the incoming signal against a library of known patterns to see if it matches something significant, like the specific frequency of a smartphone vibration. The somatosensory cortex acts as a sophisticated pattern-matching engine that favors recognizable signals over white noise. In a world where we are frequently alerted by haptic motors, the brain develops a strong template for what a notification feels like. When a stray nerve firing or the brush of a jacket occurs near the thigh, the brain may auto-correct that random input, forcing it to fit the template of a buzzing phone. This is a constructive act of the mind, where the brain prioritizes a familiar meaning over the literal, disorganized reality of the physical sensation. This tendency to impose order on the physical world is a fundamental aspect of how we navigate our environment. The brain would rather overinterpret a sensation and be wrong than miss a signal that it has deemed important through repetitive use. Because the modern human body is often in contact with various materials and subtle vibrations, the somatosensory system is constantly filtering out a massive amount of tactile noise to find the signal. When the filtering process becomes overly sensitive, the threshold for what constitutes a meaningful pattern drops significantly. A light breeze or the tension of a waistband can be misidentified as a discrete mechanical event because the brain is essentially hallucinating the structure of the vibration. This is not an error in the nerves themselves, but a high-level interpretation by the parietal lobe, which handles the integration of sensory information. The way we perceive these ghost sensations is deeply influenced by our internal expectations and the state of our nervous system at any given moment. If the brain is primed to receive a message, it will project that expectation onto any vague physical stimulus it encounters. This projection is so powerful that it can create a vivid, convincing feeling of movement where none exists. As the brain continues to scan for these patterns, it relies on specific internal messengers to modulate its sensitivity. These chemical drivers determine how much weight the brain gives to a faint sensation and how quickly it labels that sensation as a specific event. The transition from a physical touch to a perceived notification is governed by a delicate balance of neurotransmitters that sharpen our focus and heighten our tactile awareness. Dopamine functions as the primary chemical messenger for the brain's complex reward prediction system, operating as a signal for anticipation rather than just a simple feeling of pleasure. When a phone vibrates, the brain compares the actual sensory input to what it expected to happen, a process known in neuroscience as reward prediction error. If a notification arrives unexpectedly, the brain releases a surge of dopamine because the reward was better than what was predicted just moments before. This chemical spike reinforces the behavior of checking the device, effectively training the neural pathways to stay alert for the next occurrence. The brain becomes particularly hypersensitive to these signals because of a phenomenon called intermittent reinforcement. This occurs when a reward is granted at unpredictable intervals, such as a text message that might arrive in 5 minutes or 5 hours. Because the timing of the hit is unknown, the brain remains in a state of high tactile readiness, much like a biological radar system that refuses to power down. This unpredictability creates a much stronger and more persistent habit than if the rewards were delivered on a perfectly regular schedule. Within the frontal lobe, the density of dopamine D1 and D2 receptors plays a critical role in how we prioritize these digital interruptions over other physical sensations. These receptors act as gatekeepers, determining which sensory signals are important enough to break through to our conscious awareness. When these receptors are frequently stimulated by the cycle of notification seeking, they can alter the baseline sensitivity of the prefrontal cortex. This shift makes it physically more difficult for the brain to ignore a potential vibration, as the neural hardware is literally tuned to favor that specific frequency. The repetitive nature of this cycle creates a feedback loop that functions as a deep-seated biological habit. Every time a phantom vibration is felt and the device is checked, the brain is attempting to resolve a state of uncertainty. Even if no message is found, the act of checking provides a small, temporary resolution to the tension of not knowing. This loop maintains a low level of physiological arousal, as the nervous system stays primed to catch the very next signal, regardless of whether that signal is real or a ghost sensation. Understanding the mechanics of brain chemistry provides a foundation for exploring more relaxing facts about how we eventually disconnect from these patterns. By examining the way dopamine governs our attention, we can better understand the transition into a more restful state of being. Moving away from the active, seeking energy of brain chemistry allows the mind to settle into a quieter rhythm. Engaging with this science for sleep helps bridge the gap between the high-stimulation world of technology and the natural, restorative processes of the human body. The human brain possesses a remarkable capacity for physical change known as neuroplasticity, which allows individual neurons to reshape their connections in response to repetitive stimuli like the distinct pulse of a vibration. When a specific tactile sensation occurs frequently, the dendrites of sensory neurons may actually sprout new branches or strengthen existing synapses to better capture that specific incoming signal. This structural remodeling means that the brain is not a static organ, but a dynamic landscape that physically adapts to the tools we use every day. Through a process called long-term potentiation, the synapses between neurons become more efficient at transmitting signals after a period of high-frequency stimulation. In the context of tactile responses, this means that if a certain area of skin is repeatedly subjected to a vibration, the neural pathway associated with that sensation becomes greased, making it much easier for a signal to fire in the future. The threshold for activation drops, allowing even a tiny, unrelated rustle of fabric to trigger the full sensation of a digital alert. Does the mind ever truly stop scanning the environment for these subtle physical cues? Habituation serves as the biological counterweight to this sensitivity, acting as a sophisticated filtering system that allows the brain to ignore constant, unchanging sensory input. This is why you quickly lose awareness of the weight of your glasses on your nose or the continuous pressure of a waistband against your skin. The nervous system prioritizes change over stability, systematically tuning out the static background noise of your physical environment to preserve cognitive resources for more important events. While the brain successfully silences the feeling of a steady shirt sleeve, it simultaneously amplifies any sudden deviation from that baseline, such as a sharp tap or a rapid oscillation. This selective amplification is what makes the sudden buzz of a smartphone feel so much more significant than the constant touch of our clothing. The somatosensory cortex remains on high alert for these transient events, even while it remains completely blind to the persistent textures of the world around us. Consider a person who begins wearing a smartwatch for the first time, feeling the unfamiliar weight and the occasional sharp haptic pulse on their left wrist. Over the course of just a few weeks, the brain undergoes a profound shift, moving the constant pressure of the strap into the background, while simultaneously carving out a dedicated neural fast lane for the vibration. Eventually, the wearer may find themselves glancing at their bare wrist, even when the watch is charging, as the brain has been trained to expect a sensation that is no longer physically present. This training of the wrist is a perfect example of how the body incorporates external technology into its internal map of the self. As the brain builds a predictable model of when and where a vibration should occur, it begins to generate its own internal simulations of that feeling. These simulations are so vivid that they can override the actual data coming from the skin's receptors, leading to the common experience of a ghost notification during a moment of quiet. The physical structure of the sensory cortex can actually expand to devote more real estate to an area of the body that receives frequent, meaningful input. If a person carries a phone in their right pocket for years, the area of the brain representing the right thigh may become slightly more sensitive than the left. This localized hypersensitivity is a direct result of the brain's attempt to be as efficient as possible, dedicating more hardware to the parts of the body that provide the most frequent data from the outside world. Synaptic pruning also plays a role in this process, as the brain periodically clears away connections that are no longer being used to make room for new learning. If a person stops using a vibrating device for a long period, those specialized neural pathways may eventually weaken and fade. This biological reset demonstrates that while our brains are easily shaped by technology, they also possess a natural resilience and an ability to return to a more quiet, neutral baseline. Engaging with these relaxing facts about our biology helps illustrate how deeply we are connected to our environment on a cellular level. It is fascinating to realize that our very nerves are constantly being reshaped by the rhythms of our daily lives, adapting to every pulse and pressure they encounter. This quiet, ongoing transformation is one of the many ways the body prepares itself for the restorative transition into sleep. When we consider the brain's ability to learn and unlearn these patterns, the phenomenon of phantom vibrations becomes less of a glitch and more of a testament to our adaptability. We are essentially walking records of our own habits, with our nervous systems reflecting the specific frequencies of the world we inhabit. Understanding this physical reality allows the mind to drift away from the distractions of the day and settle into a state of calm, bedtime listening. The human sense of touch is far more sophisticated than a simple surface-level reaction to pressure. Deep within the layers of our skin lies a specialized group of sensory organs known as mechanoreceptors, which act as the primary translators of the physical world. Among these, the Pacinian corpuscles are uniquely designed to detect the specific, rapid oscillations produced by a vibrating smartphone or a buzzing digital notification. These microscopic structures are shaped remarkably like a sliced onion, consisting of many concentric layers of fluid-filled connective tissue wrapped around a single nerve ending. According to fundamental texts in human physiology like Guyton and Hall, these receptors are situated deep within the dermis and even the subcutaneous fatty tissue. Because they are buried so far beneath the surface, they are relatively insensitive to a gentle, steady touch or a light breeze across the skin. Instead, they require the kinetic energy of a high-frequency vibration to compress their many layers, which then triggers a mechanical pulse that reaches the central nerve fiber. This depth ensures that the brain isn't constantly overwhelmed by every minor contact, focusing instead on significant physical events like the hum of a motor or the sudden pulse of an electronic device. The way these corpuscles operate is a masterclass in biological engineering. When a vibration hits the skin, it causes the fluid between the concentric layers to shift rapidly, creating a momentary deformation of the inner nerve membrane. This physical stretching opens up tiny pores called ion channels, allowing positively charged sodium ions to rush into the nerve cell. This sudden change in electrical charge creates an action potential, which is the universal language of the nervous system, signaling to the brain that something in the environment is oscillating against the body. Once this electrical signal is generated, it begins a high-speed journey toward the central nervous system. The Pacinian corpuscle is connected to a large myelinated nerve fiber, which is essentially an insulated biological wire designed for maximum transmission speed. These fibers carry the signal at velocities of up to 70 meters per second, ensuring that the sensation of a vibration is registered by the mind almost the exact instant it occurs in the physical world. This rapid communication is vital for our ability to react to the environment in real time, whether we are feeling the texture of a fabric or the alert of a handheld device. The signal travels from the peripheral nerves in the limb or torso directly into the dorsal horn of the spinal cord. From there, it ascends through a pathway known as the dorsal column medial lemniscus system, which is a dedicated highway for precise tactile information. This pathway bypasses many of the slower processing centers of the brain, heading straight for the thalamus, which acts as the grand relay station for all sensory input. This direct routing explains why a vibration can feel so immediate and demanding of our attention, often cutting through our thoughts with singular clarity. In an earlier exploration of sensory thresholds, we touched upon how the brain decides what is a real sensation and what is merely background noise. The Pacinian corpuscle provides the biological answer to this mystery through a process called rapid adaptation. These receptors are designed to fire only at the beginning and the end of a stimulus, essentially ignoring a constant, unmoving pressure. If a vibration is steady and unchanging, the fluid layers within the corpuscle redistribute themselves to absorb the energy, causing the nerve to stop firing. This is why we can lose the feeling of a phone in our pocket until it creates a new, sudden movement that restarts the mechanical deformation. The threshold for triggering these deep-seated receptors is incredibly low for high-frequency movements, meaning they can detect vibrations as small as a few micrometers. This extreme sensitivity is what allows the brain to become so finely tuned to the specific haptic patterns of modern technology. When the brain is in a state of high anticipation, it may even prime the neural pathways, lowering the electrical barrier required for a signal to reach conscious awareness. This explains how a minor muscle twitch or the shifting of fabric can be misinterpreted as a notification. The system is so ready for a signal that it accepts a much lower level of mechanical input than usual. This sensitivity is not just a byproduct of modern life, but a highly evolved survival mechanism. In a natural environment, the ability to feel a subtle vibration might signal the movement of a predator or the buzzing of a stinging insect. The Pacinian corpuscles are our ancient early warning system, and in our current era, they have simply been repurposed to monitor the digital landscape. By understanding the deep, physical roots of these receptors, we can see that our phantom sensations are actually the result of an incredibly efficient biological system doing exactly what it was designed to do. As the body enters a period of rest, the activity within these deep receptors naturally begins to quiet down. Without the constant movement and friction of a busy day, the Pacinian corpuscles settle into a neutral state, and the high-speed pathways to the spinal cord carry fewer urgent messages. This reduction in sensory traffic allows the thalamus to shift its focus away from the external world. These relaxing facts about our internal wiring remind us that our bodies are constantly filtering and refining the world for us, even as we move toward the stillness of the night. The human brain operates as a sophisticated filter that must constantly distinguish between meaningful information and background noise. In the field of psychology and sensory biology, this process is governed by a framework known as signal detection theory. This theory suggests that our ability to perceive a stimulus depends not only on the physical intensity of the signal, but also on our internal state, expectations, and the consequences of being wrong. When you are waiting for an important message, your brain is no longer a neutral observer. It becomes a biased processor that is actively searching for a specific pattern within a sea of random physical sensations. A core component of signal detection theory involves 4 distinct outcomes that occur every time the brain evaluates a potential sensation. The first is a hit, which happens when a real signal, like an actual phone vibration, occurs and the brain correctly identifies it. A miss occurs when the phone actually vibrates, but the brain fails to register the movement because it is distracted or the stimulus is too faint. These 2 categories represent the accuracy of our sensory system when dealing with objective reality. The other 2 categories involve how we handle the absence of a signal. A correct rejection is when no vibration occurs and the brain accurately reports that nothing happened. However, the most interesting outcome in the context of phantom notifications is the false alarm. This happens when there is no actual signal, yet the brain mistakenly concludes that a vibration has occurred. According to the principles outlined in many foundational texts like open stack psychology, the frequency of these false alarms is directly tied to our internal criterion for what constitutes a signal. If the brain is in a state of high anticipation, it lowers its internal threshold for what it considers a valid notification. This means that a very small amount of neural noise, such as a muscle twitch or the brush of a jacket, is suddenly enough to trigger a false alarm. The brain decides it is better to have a false alarm than to suffer a miss on an important communication. This shift in the internal criterion explains why you might feel a ghost notification more often when you are expecting an urgent call or waiting for a specific social interaction. The biological cost of a miss is often perceived as higher than the cost of a false alarm in our modern, hyper-connected environment. Because we value the information coming through our devices, our nervous system adapts by becoming hypersensitive. This is a classic example of how top-down cognitive processes, our thoughts and expectations, can physically alter the sensitivity of our bottom-up sensory processing. Even without a physical change in the skin's receptors, the brain's decision-making centers become more likely to say yes to any ambiguous sensation. As we consider how the mind sorts through these subtle impulses, it becomes clear that our perception is a delicate balance of probability and biological intent. The constant tension between being alert and being at rest shapes how we experience the world around us. Science for sleep often looks at how we can return these elevated thresholds to a more neutral baseline. When we understand that a phantom vibration is simply a false alarm in a well-functioning signal detection system, the sensation loses its power to startle us. It is merely a sign that the brain is doing its job, albeit with a bit too much enthusiasm. This realization allows the nervous system to begin the transition from a state of high alert monitoring to one of quiet observation. The brain's map of the body is not a static image, but a living, breathing geography that changes based on how we use our limbs and where we direct our attention. Within the somatosensory cortex, specific regions are dedicated to processing touch from different parts of the skin. If you always keep your phone in your right front pocket, the area of the brain representing that specific patch of skin on your thigh may become more electrically loud or sensitive. This localized increase in neural representation makes that area a prime candidate for the false alarms described in signal detection theory. Research cited in textbooks like Campbell Biology highlights how sensory systems are tuned to detect change rather than steady states. This is why we don't feel the constant pressure of our shoes after a few minutes, but we immediately notice a small pebble inside them. A phone vibration is a sudden change in the environment, and our brains are evolutionarily hardwired to prioritize sudden changes over constant backgrounds. Phantom vibrations take advantage of this hardwiring, slipping through the filter because they mimic the exact type of change our brains are programmed to find important. When the environment is quiet and the body is still, the ratio of signal to noise changes significantly. In a loud, moving vehicle, a small vibration might be missed entirely. But in the stillness of a bedroom, the background noise is so low that even the smallest internal neural firing can be interpreted as an external signal. This explains why many people experience ghost notifications most frequently when they are beginning to wind down for the evening. The brain, lacking external distractions, begins to amplify its own internal static. This internal amplification is a testament to the brain's incredible power as a predictive engine. It is not just waiting for the world to happen to it. It is actively guessing what will happen next. By understanding these mechanisms of signal detection and cortical mapping, we can appreciate the complexity of the human experience. These relaxing facts help us see that our technology has not broken our brains, but rather, our brains are so adaptable that they have integrated these new digital signals into our ancient sensory architecture. Deep within the parietal lobe of your brain lies a specialized strip of tissue known as the somatosensory cortex, which serves as a living, dynamic map of your entire body. This thin ribbon of neurons is responsible for processing every touch, temperature change, and vibration you feel from your toes to your forehead. Interestingly, this internal map does not represent your body parts based on their actual physical size, but rather by how sensitive they are and how much sensory data they provide to the brain. Scientists often illustrate this concept using a figure called the sensory homunculus, a distorted human shape where the hands, lips, and face are massive, while the torso and legs are quite small. This visual tool, frequently cited in foundational texts like Gray's Anatomy, demonstrates that your brain dedicates vast amounts of neural real estate to areas requiring fine motor control or high tactile sensitivity. Because the thigh and the wrist are common places to keep or wear digital devices, the brain maintains specific clusters of neurons dedicated to monitoring those exact patches of skin with incredible precision. How does the mind actually determine where the physical boundaries of the body end and the outside world begins? This question sits at the heart of why we experience phantom sensations, as the brain is constantly recalibrating its map based on the tools and objects we use most frequently. Neuroplasticity allows the somatosensory cortex to be flexible, meaning that the more often a specific area of skin is stimulated, the more sensitive that area can become over time. If you carry a smartphone in the same pocket every day for years, your brain may actually expand the cortical representation of that specific patch of skin on your leg to better monitor for incoming signals. This expansion means that the neurons responsible for your thigh are essentially leaning in, waiting for the familiar buzz of a notification with heightened readiness. In this state of increased cortical devotion, the brain becomes so efficient at detecting vibrations that it sometimes misinterprets the rustle of fabric or a minor muscle twitch as a digital alert. The device has effectively become a functional extension of your body schema, integrated into the very map the brain uses to navigate the physical world. As you rest, these neural maps begin to quiet down, shifting away from the high alert status required during a busy day of communication. The brain's ability to reshape itself in response to your environment is a hallmark of human biology, showing just how deeply our habits influence our physical structure. These relaxing facts about our internal architecture remind us that even our most modern frustrations are rooted in the brain's magnificent capacity for adaptation. Science for sleep often reveals that our perceived reality is a delicate balance between what our nerves feel and what our brain expects to feel. By dedicating more neural resources to the areas where we expect to receive information, our brains are simply trying to ensure we don't miss anything important in a fast-paced world. This process of cortical mapping is a silent, ongoing miracle that happens every moment, even as the body prepares for deep and restorative stillness. While the phantom vibration of a phone against the skin is a physical sensation, the brain also creates similar illusions through the sense of hearing. This shift from touch to sound happens because the mind is always scanning the environment for familiar patterns that signal social connection or important information. When you expect a message, your auditory system enters a state of high readiness, making you prone to hearing ghost pings even in total silence. The human brain is an extraordinary filter that constantly sorts through a sea of background noise to find meaningful signals. In environments with steady, low-level sounds like a running fan or a distant air conditioner, the brain sometimes misidentifies random frequencies as a specific notification chime. This process occurs because the mind prefers to find a familiar pattern in the noise rather than dismiss it as meaningless static. Scientific research into auditory perception shows that the brain is particularly sensitive to the specific frequency range used by most modern smartphone alerts. According to studies on psychoacoustics, many device manufacturers design notification sounds to sit between 2,000 and 5,000 Hz. This is the exact frequency range where human hearing is most sensitive, as it is the same range where the most critical sounds of human speech and infant cries are found. The primary auditory cortex is the region of the brain responsible for the initial processing of sound, but it works closely with the association areas to interpret what those sounds mean. These association areas are highly influenced by recent memories and strong expectations, creating a top-down effect on your hearing. If you have been checking your device frequently, these neurons stay primed to recognize the specific melody of your ringtone, even if the actual air vibrations aren't there. This phenomenon is often most noticeable when you are in a quiet environment or performing a repetitive task like washing dishes. The sound of running water creates a broad spectrum of white noise that contains almost every frequency the human ear can detect. Because all the ingredients of your notification sound are present in the splashing water, your brain may momentarily pluck them out and assemble them into a ghost notification. The brain's tendency to find these patterns is a survival mechanism that has been repurposed for the digital age. In nature, missing a subtle sound could mean missing a potential threat or an opportunity for food, so the auditory system is biased toward hearing something that isn't there rather than missing something that is. This bias ensures that your ancestors could hear a predator in the rustle of dry leaves, even if it was just the wind. In the modern world, this same biological hardware treats a digital ping with the same level of urgency as a physical sound in the woods. Because the social reward of a message is often linked to a hit of dopamine, the brain becomes highly motivated to detect that sound as often as possible. This creates a feedback loop where the more you value the notification, the more likely you are to hear it when the room is actually quiet. Recent studies in neuroscience suggest that people who experience high levels of social anxiety or workplace stress are significantly more likely to experience these auditory illusions. The brain's gain control is turned up, meaning it amplifies weak signals in an attempt to ensure nothing is missed during periods of high demand. This state of heightened sensitivity is a testament to how hard the mind works to keep us connected to our social circles. The auditory cortex does not work in isolation. It is constantly communicating with the emotional centers of the brain to determine which sounds deserve your attention. When a ghost notification occurs, it is often accompanied by a brief moment of focused alertness as the brain redirects all its resources to confirm the sound. Once you realize the sound was an illusion, the brain slowly resets its baseline and returns to its resting state. Interestingly, these ghost sounds are often identical in pitch and rhythm to the actual settings on your device, showing how deeply the brain has encoded these digital signatures. The more unique and distinct a notification sound is, the more easily the brain can accidentally reconstruct it from background noise. This level of neural encoding shows that our technology is not just in our pockets, but is deeply integrated into our sensory processing systems. As the body begins to settle into a state of rest, the need for this constant monitoring begins to fade. The brain shifts away from the external world and starts to prioritize internal processes, allowing the auditory filters to relax and become less reactive. This transition is a natural part of the daily cycle, moving from a state of high alert pattern recognition toward a peaceful and quiet internal environment. Understanding that these ghost pings are a byproduct of a highly efficient and protective brain can make them feel less intrusive. They are simply evidence of a mind that is exceptionally good at finding meaning in the world around it. By acknowledging the science behind these sounds, we can appreciate the incredible sensitivity of our own hearing and the complex way our brains navigate a world filled with both natural and digital signals. Modern haptic engines, specifically those known as linear resonant actuators, are designed to create tactile feedback by accelerating a magnetic mass back and forth against a spring mechanism. This internal movement generates a precise resonance that mimics the natural rhythmic pulses our biological nerves are evolutionarily tuned to recognize in the physical world. By oscillating at specific frequencies, these devices can bypass the general noise of daily life and speak directly to the mechanoreceptors in our skin, creating a sensation that feels intentional and organic rather than mechanical. These pulses feel surprisingly familiar to the human touch. By the year 2026, haptic technology has advanced to a state of high-fidelity sophistication, offering frequency ranges that allow for the simulation of complex physical textures and subtle microvibrations. Modern devices can now produce distinct tactile signatures that differentiate between the heavy thud of a notification and the light, airy tap of a message, using a spectrum of vibrations that were once impossible to achieve. This level of precision ensures that the brain receives a clear, unmistakable signal that stands out against the backdrop of other physical sensations, like the texture of clothing or the movement of air. The mind begins to adapt to this complex digital language. Neuroplasticity is the remarkable ability of the brain to reorganize its physical structure and synaptic connections in response to the repetitive stimuli it encounters in its environment. When a person carries a smartphone every day, the brain begins to treat the specific vibration patterns of that device as a primary sensory input, eventually carving out dedicated neural pathways to process these signals more efficiently. This adaptation means that the brain is not just reacting to a vibration, but is actively learning to prioritize it, making the sensation feel more significant than a random muscle twitch. How does the brain decide where the body ends and the technology begins during these moments of deep integration? This phenomenon is driven by the brain's ability to incorporate external objects into its internal body schema, which is the neural map used to track the position and boundaries of our physical limbs. When a tool or device is used consistently and provides reliable sensory feedback, the parietal cortex can actually expand this map to include the device as a functional extension of the self. This integration is so profound that the brain begins to monitor the health and status of the device with the same unconscious vigilance it uses to monitor a finger or a hand. Our tools eventually become extensions of our physical selves. Scientific research, including studies documented in major textbooks like Campbell Biology, indicates that the premotor cortex processes frequently used tools using the same neural hardware that governs biological appendages. This means that when your phone vibrates, your brain is not just perceiving an external event, but is interpreting a change in what it perceives to be a part of its own body. This seamless merging of man and machine explains why a phantom vibration can feel as real as a physical itch. The brain is simply checking in on a part of the body schema it has been trained to monitor. This deep integration makes the device feel like a permanent part of us. The somatosensory homunculus, which is a physical map of the body within the brain's cortex, is highly malleable and can shift its proportions based on the frequency of sensory input received from different areas. If a specific patch of skin on the thigh or wrist is frequently stimulated by the haptic engine of a mobile device, the corresponding area in the brain's map may become slightly more sensitive or take up more cortical space. This remapping is a perfect example of how our modern environment can physically reshape the landscape of our nervous system to better suit the demands of constant connectivity. The brain is an organ that thrives on these subtle physical shifts. During periods of bedtime listening, the brain begins the necessary process of sensory attenuation, where it gradually withdraws its focus from these extended digital boundaries. As the body enters a state of rest, the brain turns its attention inward, allowing the neural pathways that monitor for haptic signals to enter a dormant phase. This natural transition helps the body schema return to its original, unaugmented state, ensuring that the mind can detach from the external world and focus on the quiet internal processes required for a restorative night. This transition is essential for finding true mental stillness. When the brain finally disconnects from these external signals, it undergoes a process called synaptic pruning of short-term patterns, which helps clear the day's sensory clutter. This clearing allows the nervous system to reset its baseline sensitivity, ensuring that it doesn't remain in a state of permanent hyperalertness to digital cues. By allowing the brain to release its grip on these technological extensions, we provide the somatosensory cortex with the space it needs to recover and maintain its primary role of monitoring our natural biological functions. Understanding this biological flexibility reveals the true power of the human mind. The incredible predictive power of the brain means that it is always looking for ways to streamline its work, even if that involves turning a piece of glass and metal into a part of our neural identity. By recognizing that these phantom sensations are a result of our brain's high-speed adaptability, we can view them as a sign of a healthy, functioning nervous system. This perspective allows us to appreciate the complex dance between our ancient biological hardware and the modern digital world we navigate every day. Modern life often places the human nervous system into a state of sustained hypervigilance, where the brain remains perpetually prepared for incoming digital signals. This psychological state occurs when the mind assigns a high priority to external notifications, keeping the sensory pathways in a condition of constant readiness. Within the framework of psychology, this is known as a state of heightened arousal, where the baseline level of attention is shifted upward to ensure that no relevant information is missed. Maintaining this low-level alert state requires a continuous expenditure of metabolic energy by the brain's frontal lobes. The biological cost of this vigilance is subtle but measurable, as the brain must divert resources away from deep, reflective processing to power the systems responsible for monitoring environmental cues. Over time, this constant scanning can lead to sensory fatigue, where the nerves become less efficient at distinguishing between a true signal and background noise. The autonomic nervous system is the primary mechanism responsible for balancing these states of alertness and recovery. It operates through two main branches known as the sympathetic and parasympathetic systems, which act like a sophisticated internal seesaw. When we are waiting for a vibration or a chime, the sympathetic nervous system maintains a mild degree of tone, keeping the heart rate and muscle tension at a level optimized for quick reactions. In contrast, the parasympathetic nervous system is responsible for the body's rest and digest functions, working to lower the heart rate and promote internal maintenance. For the body to achieve a state of true physiological recovery, the parasympathetic branch must become dominant, allowing the sympathetic system to scale back its activity. Scientific observations in clinical settings show that a prolonged shift towards sympathetic dominance can temporarily alter how the brain processes tactile information from the skin. Hypervigilance essentially narrows the window of sensory filtering, making the brain more likely to report a sensation that isn't there. This is not a sign of a malfunctioning mind, but rather an indication of a highly responsive system that has successfully adapted to a fast-paced environment. The brain simply treats the potential for a notification as a significant event, much like it would treat a physical touch from another person in a social setting. This persistent state of readiness can cause the brain to misinterpret the internal rhythms of the body as external prompts. Minor changes in blood flow or the natural pulsing of an artery near the surface of the skin can be caught in the net of this heightened awareness. Because the nervous system is looking for a specific frequency of vibration, it may categorize these internal biological movements as the phantom signals we often feel in our pockets. The density of the nervous system's monitoring network means that even at rest, the brain is processing thousands of data points every second. When hypervigilance is present, the threshold for what constitutes an important data point is lowered, leading to the frequent false alarms associated with phantom vibrations. This mechanism is a testament to the brain's desire to stay connected to its surroundings, prioritizing speed and sensitivity over perfect accuracy. By understanding the interplay between the sympathetic and parasympathetic systems, it becomes clear that these sensations are a natural byproduct of a busy life. The nervous system is simply doing its job by staying alert to the cues it has been trained to value. Shifting back into a parasympathetic state allows the brain to widen its filters again, returning the body to a baseline of calm and focused internal awareness. The transition between wakefulness and the first stages of sleep is a unique biological period known as the hypnagogic state. During this window, the brain begins to withdraw its attention from the external world to focus on internal processes. As the prefrontal cortex relaxes its grip on logic and sensory filtering, the mind becomes highly susceptible to vivid imagery and unusual physical sensations. Many people report feeling a sudden, sharp vibration or a distinct ghostly notification just as they are about to drift off. This occurrence is a hallmark of the hypnagogic phase, where the boundaries between memory, expectation, and reality become temporarily thin. In this drifting state, the brain waves begin to shift from the fast, jagged rhythms of beta and alpha activity into the slower, more rhythmic patterns of theta waves. Theta waves are associated with deep relaxation and the early stages of light sleep, but they also mark a period of increased creativity and fragmented sensory processing. As the brain settles into this slower frequency, it may struggle to categorize the final flickers of neural activity from the day. A tiny muscle twitch or a pulse of blood can be amplified by the shifting brain chemistry, leading the somatosensory cortex to interpret the movement as a familiar technological signal. The biology of the sleeping brain reveals that our sensory systems do not simply shut off. Instead, they change their mode of operation. During the descent into sleep, the thalamus acts as a gatekeeper, deciding which signals from the body are allowed to reach the conscious mind. If the brain has spent the day in a state of high alert for notifications, the thalamus may remain primed to let through any data that feels like a vibration. This explains why tactile hallucinations can spike right before falling asleep, as the gatekeeper is still scanning for specific patterns even as the rest of the system prepares for rest. These phantom pings during the onset of sleep are often a result of the brain's attempt to make sense of neural noise. As neurons in the brainstem begin to inhibit the body's motor signals to prevent us from acting out our dreams, small electrical leaks can occur. These leaks can stimulate the areas of the brain responsible for touch, creating a sensation of movement or pressure that feels remarkably real. Because the modern mind is so accustomed to the specific haptic pulse of a smartphone, the brain often selects that specific template to explain the random neural firing it experiences in the dark. Have you ever wondered why a phantom vibration feels more intense when the room is completely silent and still? This happens because the brain's signal-to-noise ratio changes dramatically when external distractions are removed. In a busy environment, the brain ignores thousands of minor skin sensations, but in the quiet of a bedroom, every tiny mechanical shift in the body is magnified. The absence of actual sensory input causes the brain to turn up the volume on its internal sensors, making it much more likely to generate a ghost notification from the simplest biological source. Science for Sleep research suggests that the persistence of these sensations is linked to the way the brain consolidates memories during the night. As the hippocampus and cortex begin the work of filing away the day's events, the repetitive task of checking a device may be replayed in a fragmented way. This replay can trigger the physical memory of a vibration, leading to a tactile hallucination that feels as though it is happening in the present moment. It is a fascinating example of how our daily habits leave physical imprints on our neural architecture, surfacing just as we let go of the day. The phenomenon of hypnagogic jerks, or sudden muscle starts, can also play a role in these nightly phantom signals. When a large muscle group undergoes a brief, involuntary contraction during the transition to sleep, the brain may misinterpret the subtle aftershock of that contraction as a vibrating phone. This misinterpretation is more common if the device is usually kept on a bedside table or under a pillow, as the brain maintains a spatial map of where notifications usually occur. Even without the device being physically present, the brain's internal map remains active, ready to assign meaning to any twitch in that specific area. As the body enters deeper stages of sleep, these phantom sensations generally fade away as the brain moves past the threshold of theta activity. The internal world becomes more stable, and the sensory gatekeeper of the thalamus becomes more restrictive, shielding the mind from minor physical interruptions. Understanding this process allows us to see these ghost notifications not as disruptions, but as signs of the brain's incredible dedication to monitoring its environment. It is a gentle reminder of the complex transition the mind undergoes every night as it moves from the digital demands of the day into the restorative silence of deep rest. The human brain does not simply sit and wait for the world to happen to it. Instead, it is an active engine of prediction, constantly guessing what the next physical sensation will be before it even occurs. This internal anticipation creates a fascinating tug-of-war between two distinct ways of perceiving reality. The first method is known as bottom-up processing, which begins at the very edges of the body. In this flow of information, the specialized receptors in the skin detect a physical change, like a genuine phone vibration, and send a signal up through the spinal cord. It is a data-driven process where the physical world dictates what the mind experiences. The second method, called top-down processing, works in the opposite direction. Here, the brain's higher cognitive centers use past experiences and current expectations to tell the sensory system what it should be feeling. This internal narrative is so powerful that it can frequently override the actual data coming in from the skin. When these two systems clash, the result is often a phantom notification. The brain is so convinced that a message is arriving that it preemptively activates the sensory pathways associated with touch. This mental shortcut allows the mind to prioritize information it deems important, even if that information does not exist in the physical environment. Does the mind actually allow us to feel things before they truly happen? This question highlights the incredible efficiency of top-down processing in our daily lives. By predicting sensations, the brain saves an immense amount of energy and reduces the time it takes to react to the world. It essentially creates a simulation of reality that runs just a few milliseconds ahead of the actual physical events. The physical speed of this communication is remarkably consistent across the human nervous system. According to established neurobiology, large myelinated nerve fibers, such as those responsible for touch and vibration, carry impulses at speeds ranging from 80 to 120 meters per second. This rapid transit ensures that the gap between a physical touch and the brain's awareness of it is nearly instantaneous. Despite this incredible speed, the top-down system often wins the race. Because the brain can initiate a feeling based on a thought or a habit, it doesn't have to wait for a signal to travel from the thigh or the wrist. It simply generates the sensation internally, pulling from a library of stored tactile memories. This ability to override the physical nerves is a testament to the dominance of the cerebral cortex over basic anatomy. If the brain expects a vibration because it is a high-stress day or a specific time of evening, it can lower the firing threshold of sensory neurons. This makes them much more likely to misfire in response to the simple movement of clothing or a shift in posture. When the brain is in this state of high expectation, the sensory gatekeepers become less discriminatory. They begin to accept any minor electrical noise or muscle tremor as a hit for a notification. This transition from objective sensing to subjective predicting is a core part of how we navigate a world filled with constant digital stimuli. In a very real sense, the phantom vibrations we feel are not errors, but rather the overperformance of a highly sophisticated survival mechanism. The brain would rather report a vibration that isn't there than miss a signal that it believes is vital for social or professional connection. This reveals a deep biological truth about the importance of communication in the modern human experience. As the mind begins to settle, the influence of top-down processing usually starts to wane. The heavy focus on external signals gives way to internal maintenance and the quiet rhythms of the body. The transition is a slow fading of the digital map the brain carries throughout the day. Relaxing facts about the somatosensory system show that this balance is delicate. Even a small change in environment can shift how much we rely on our expectations versus our actual physical senses. It is a constant calibration that the nervous system performs without any conscious effort on our part. Science for Sleep explores how this calibration changes as we move toward rest. The brain slowly relinquishes its grip on top-down predictions, allowing the body to return to a baseline state of calm. This shift is essential for moving away from the always-on nature of modern technology. As the dominance of the predictive brain eases, the physical nerves finally get a chance to go quiet. The internal simulation of the world shuts down for the night, leaving only the soft, rhythmic reality of the present moment. It is in this space that the phantoms of the day finally disappear. The brain often misinterprets common physiological events as digital signals because it is constantly scanning for specific frequencies. This process of misattribution occurs when a minor bodily sensation shares the same rhythmic profile as a vibrating phone motor. Because the somatosensory cortex is primed to receive a notification, it frequently rebrands a random biological twitch as a deliberate mechanical alert. A primary culprit in these phantom sensations is the localized muscle fasciculation, which is a tiny, involuntary contraction of a single motor unit. These flickers of movement are caused by spontaneous nerve impulses that trigger a small bundle of muscle fibers to fire. When these twitches happen in the large muscles of the thigh, where a phone is often kept, the frequency of the muscles ripple closely mimics the rapid oscillation of a linear resonant actuator. Beyond internal muscle movement, the simple physics of friction against the skin provides another source of sensory confusion. The human body is covered in thousands of tiny hair follicles, each equipped with a delicate nerve ending that acts as a motion detector. When fabric moves across these hairs, it creates a series of rapid, microvibrations that the brain must filter and identify. Consider the experience of a person wearing loose-fitting denim while walking through a quiet hallway. As the heavy fabric shifts with each step, it creates a rhythmic brushing against the skin of the leg that feels remarkably like a buzzing device. In this moment, the mechanoreceptors in the dermis send a flurry of signals that the brain, expecting a message, incorrectly maps onto the mental image of a smartphone. Is it possible that our physical clothing has become a permanent extension of our sensory landscape? This interaction between textiles and skin is a constant source of false alarms in the nervous system. The brain is so efficient at pattern recognition that it would rather over-identify a sensation than miss a potentially important social cue. By understanding these tiny mechanical triggers, we can see how easily the mind constructs a digital reality out of simple, earthly friction. While it may seem that these ghost notifications are a unique product of the digital age, they are actually a fundamental expression of how the human brain adapts to any consistent environmental stimulus. Long before the first smartphone was engineered, people reported nearly identical sensory illusions linked to the primary tools of their era. This suggests that the tendency to feel things that aren't there is a hardwired biological feature rather than a modern technological glitch. During the 1990s, a widespread phenomenon known as phantom pager syndrome affected millions of professionals who carried beepers on their waistbands. Doctors and technicians frequently reported a distinct buzzing sensation against their hip, only to find the device silent and dark upon inspection. This era proved that the brain does not need a complex touchscreen or a high-speed internet connection to develop a hypersensitivity to a specific vibration frequency. The mind possesses an incredible ability to incorporate external objects into its own internal map of the body. When a tool becomes essential for communication or work, the somatosensory cortex begins to treat that tool as if it were a literal limb or a patch of skin. This neurological integration is so deep that the brain remains on high alert for any signal that the tool is active, even when the person is trying to fall asleep in a quiet room. Historical records from the mid-19th century reveal that telegraph operators experienced a strikingly similar auditory version of this phantom effect. After spending 10 or 12 hours a day listening to the rhythmic clicking of Morse code, operators often heard the ghostly tapping of messages in the silence of their own homes. The auditory cortex had become so attuned to those specific patterns that it began to manufacture them out of the ambient noise of a ticking clock or a crackling fire. This phenomenon is not limited to sounds or vibrations, but extends to the very sense of balance and motion. Sailors who spend long periods at sea often experience a condition called mal de débarquement, or the sickness of disembarkation, once they return to solid ground. They feel the earth beneath them swaying and rolling as if they were still on the deck of a ship, because the brain has calibrated its baseline for reality to a moving environment. In these cases, the vestibular system is still trying to compensate for waves that are no longer there. The brain continues to send correction signals to the muscles to keep the body upright on a moving surface, resulting in the persistent sensation of rocking. It takes days or sometimes weeks for the internal equilibrium to accept that the environment is now stable and motionless. The human nervous system is essentially a predictive engine that is always trying to stay one step ahead of the next sensation. By projecting these expectations onto the physical world, the brain ensures that it is never caught off guard by an important change. This predictive nature is what allows us to process complex information rapidly, but it also means we occasionally perceive a ghost in the machine. When we consider these historical examples, the modern experience of a vibrating phone in an empty pocket feels less like a medical concern and more like a testament to our adaptability. Whether it is the clicking of a telegraph or the swaying of a ship, the mind is always looking for patterns to help it navigate the world. These relaxing facts about our sensory history show that we have always lived in a world where the line between internal expectation and external reality is beautifully blurred. Is it possible that our internal chemistry shifts to make these phantoms even more vivid during times of high focus? This persistent state of readiness is a carryover from an evolutionary past where missing a tiny physical cue could have serious consequences. Our ancestors survived by being hyper-aware of the smallest snap of a twig or the lightest brush of a leaf against their skin. In the modern world, we have simply redirected that ancient, life-saving sensitivity toward the digital signals that connect us to our social circles. The brain's reward centers also play a significant role in maintaining these sensory loops over long periods. Every time a real notification arrives, a small pulse of dopamine is released, reinforcing the neural pathways associated with that specific sensation. Over time, the brain becomes so eager for that chemical reward that it begins to hallucinate the trigger just to see if the reward might follow. As the body begins to wind down for the night, these sensory expectations can sometimes become even more pronounced. This is because the brain is no longer distracted by the heavy flow of external information that defines our waking hours. In the stillness of the evening, a tiny muscle twitch or the slide of a bedsheet can easily be misread as a digital alert. Using science for sleep allows us to view these strange occurrences as simple biological echoes. When you feel a phantom vibration while resting, it is merely your somatosensory cortex performing a routine check of its environment. It is a sign that your brain is functioning exactly as it should, scanning for patterns and staying prepared for the next interaction. Understanding the deep history of these sensations helps to demystify the experience and reduce any lingering tech anxiety. From the high-seas sailors of the past to the smartphone users of today, the human experience has always been defined by this strange, wonderful ability to feel the world through our tools. By acknowledging this, we can let go of the need to check the device and allow the mind to settle into a deep, uninterrupted state of rest. The human body is governed by a complex internal chemistry that dictates how we perceive the world around us. Cortisol, often referred to as a primary stress hormone, plays a vital role in regulating sensory sensitivity and alertness. Produced by the adrenal glands, this steroid hormone fluctuates throughout the day to help the body manage its energy demands and environmental responses. When cortisol levels rise, the nervous system enters a state of heightened awareness, which can significantly alter the way skin receptors process tactile information. The endocrine system and the nervous system work in a constant, silent partnership, to maintain a baseline of physical sensation. Cortisol acts as a modulator, traveling through the bloodstream to reach various tissues, including the peripheral nerves in our limbs. Research published in journals like Psychoneuroendocrinology suggests that higher concentrations of cortisol can lower the threshold at which a nerve fiber fires. This means that a stimulus that might usually be ignored by the brain suddenly becomes noticeable and distinct. In a state of mild physiological arousal, the brain becomes much more likely to report a sensation that isn't actually there. This phenomenon is closely tied to how cortisol sharpens our focus on potential signals while decreasing our ability to filter out background noise. When the body is under even slight pressure, the sensory gates in the thalamus swing wide open. This internal chemical shift can turn a simple muscle twitch or the friction of a sleeve into a convincing imitation of a digital vibration. Does the specific chemical balance of our blood at any given moment fundamentally change the reality of what we feel against our skin? The relationship between cortisol and sensory perception is a finely tuned evolutionary mechanism designed for protection. In high-stakes environments, being able to feel the slightest brush of an object can be the difference between safety and a missed threat. In our modern lives, this same mechanism is frequently triggered by the subtle, ongoing demands of work and social connectivity. The result is a body that is biologically primed to detect signals, even when the environment is perfectly still. When cortisol levels remain elevated, the peripheral nervous system can enter a state of wind-up, where neurons become increasingly reactive to repetitive stimuli. This process, known as sensitization, ensures that the brain stays informed about any persistent physical contact. For someone who carries a smartphone in the same pocket every day, this sensitization can create a lasting neural imprint. The brain learns to prioritize that specific area of the thigh, making it the most likely place for a phantom sensation to manifest. Science for sleep reveals that as the evening progresses, cortisol levels naturally begin to dip to allow the body to transition into a state of recovery. This decline is essential for the nervous system to move from an external focus to an internal one. However, if a person experiences a sudden spike in cortisol due to a late-night email or a lingering thought, the sensory system can briefly reactivate. This sudden shift in chemistry is often what triggers a final phantom vibration, just as the mind is trying to drift away. The interplay between hormones and touch is a testament to the incredible plasticity of the human experience. Our skin is not just a passive barrier, but a dynamic interface that changes its sensitivity based on our internal state. By understanding that cortisol can amplify these tiny physical echoes, we can view phantom notifications as a simple byproduct of a very efficient biological system. It is a sign that the body is simply doing its job of staying vigilant and responsive to the world. As we move toward a deeper understanding of these internal rhythms, the mind begins to see the logic behind every phantom ping and ghostly buzz. These sensations are not glitches, but rather the result of a sophisticated chemical dance happening within the cells. This realization allows the body to settle, knowing that the vibrations are just the nervous system's way of processing the day's data. With the cortisol fading and the senses softening, the path to a quiet, undisturbed rest becomes clear. I hope you find these relaxing facts helpful as you prepare for a peaceful night of rest. Please consider subscribing to join us for more scientific explorations. The quiet brilliance of the human brain lies in its ability to anticipate the future while gently letting go of the present. The human brain possesses a remarkable capacity for neuroplasticity, which allows it to unlearn the very patterns of phantom vibrations it once worked so hard to establish. When a person consciously chooses to move their mobile device to a different pocket or switches it to a completely different side of the body, the brain is forced to reevaluate its sensory expectations. This simple change disrupts the established neural pathways that were primed to detect a specific frequency in a specific location. Over time, the lack of reinforcing stimuli causes the somatosensory cortex to decrease the amount of real estate it has dedicated to that phantom hotspot, eventually quieting the false alarms. This process of unlearning is driven by a biological mechanism known as synaptic pruning, where the brain systematically weakens and removes connections that are no longer being used. When the expected vibration fails to occur day after day in the old location, the neurons that were once hypervigilant begin to lose their high-priority status. This is not an instantaneous change, but rather a gradual fading of a learned behavior as the brain realizes the old pattern is no longer relevant to its current environment. Scientific studies in journals like Nature suggest that this pruning is an essential part of maintaining an efficient nervous system, ensuring that we do not remain haunted by outdated habits. The timeline for resetting these somatosensory baselines can vary, but many individuals report a significant reduction in phantom sensations within just a few weeks of changing their habits. During this period, the brain undergoes a recalibration phase where it widens its sensory filters, becoming less reactive to the tiny muscle twitches or fabric shifts that it previously misidentified. As the threshold for what constitutes a notification is raised back to a normal level, the peripheral nerves return to a state of quiet equilibrium. This reset allows the body to exist in a space of tactile neutrality, where the skin is once again just skin, rather than a waiting receiver for digital data. Relaxing facts about our biology often remind us that the mind is not a static machine, but a living, breathing landscape that can be reshaped through intentional rest. By providing the nervous system with periods of sensory deprivation, such as leaving a device in another room during the evening, we give the brain the silence it needs to perform its nightly maintenance. This absence of input is a signal to the somatosensory system that it can finally stand down from its watch. In this state of reduced demand, the firing rates of our neurons slow down, mirroring the gentle, rhythmic pulses of a body moving toward deep sleep. As the pacing of these internal processes begins to lengthen, the entire nervous system starts to mirror this slower, more deliberate cadence. The heart rate finds a steady, low-frequency rhythm, and the muscles in the hands and thighs, the most common sites for phantom vibrations, finally release their latent tension. This physical softening is the result of the brain's inhibitory neurotransmitters taking the lead, dampening any stray electrical signals that might otherwise cause a flicker of sensation. The world of digital interruptions fades into the background, replaced by the profound, steady reality of the physical self at rest. The biology of habit reversal is a testament to the brain's enduring wisdom and its desire for balance above all else. It knows when to lean into a new technology, and it knows exactly how to let go when that technology is no longer present. This ability to return to a baseline of peace is a built-in feature of our evolution, ensuring that we are never permanently stuck in a state of high alert. As the final remnants of the day's notifications dissolve, the mind prepares itself for a long, uninterrupted period of restoration, where the only vibrations are the soft, natural movements of breath. Every cell in the body participates in this transition, moving away from the frantic energy of the day and toward the restorative silence of the night. The somatosensory cortex, once buzzing with the activity of 1,000 imagined pings, now settles into a quiet, dark expanse. This internal quietude is the ultimate goal of the brain's adaptive powers, providing a sanctuary where the self can simply exist without the need for response or reaction. In this stillness, the true science for sleep begins to take hold, guiding the consciousness into a deep and effortless drift. The human brain functions as an incredible organ of anticipation, constantly generating internal models to predict the physical world before it even touches the skin. This predictive power allows us to navigate complex environments, but it also creates the quiet mystery of sensations that exist only within our own neural architecture. Through the lens of modern neuroscience, we see how the brain's quest for connection has repurposed ancient survival mechanisms for the digital age. Our ancestors once scanned the horizon for subtle movements, a task driven by the same dopaminergic pathways that now alert us to a potential notification. These chemical rewards create a heightened state of readiness, sensitizing the mechanoreceptors in our skin to the smallest flickers of movement or pressure. Whether it is the rustle of a leaf or the phantom vibration of a phone, the biological hardware remains remarkably consistent across thousands of years of human evolution. Our technology has changed rapidly, yet the somatosensory cortex continues to process these new inputs using the same fundamental principles of pattern recognition and signal detection. This bridge between our biological past and our technological present highlights the profound adaptability of the human nervous system. When we consider the intricate dance of neurons and neurotransmitters, we begin to see phantom notifications not as errors, but as evidence of a brain that is deeply attuned to its environment. This sensitivity is a hallmark of our species, reflecting a mind that is always searching, always learning, and always ready to engage with the world. As the day ends, the brain finally begins to dial down these predictive models, allowing the heightened state of digital many-tasking to dissolve into a singular, quiet focus. The transition into rest is a physiological necessity, a time for the brain to prune away the noise of the day and reinforce the pathways that truly matter. Understanding these relaxing facts about our own biology helps us appreciate the complexity of the silent processes happening beneath the surface of our conscious awareness. Every phantom pulse and every ghost notification is a small reminder of the sophisticated machinery that keeps us connected to our surroundings. As you continue to explore the wonders of the natural world and the mechanics of the mind, consider joining our community for more peaceful journeys into science by subscribing to the channel. The true beauty of the resting mind lies in its ability to transform the day's curiosity into the quiet wisdom of a deep and restorative sleep.